Okay, so now that we know about the types of chemical reactions as they relate to energy transfer, we're going to talk about ways that chemical reactions can either be sped up or slowed down. So our essential question is infer what factors determine the speed of chemical reactions. So this is learning target 43. Evaluate what factors will affect the rate of reaction. So in order for chemicals to react, you have to have collisions. Molecules must collide, and these collisions must be strong in order for the chemical reactions to occur. So reactions occur when particles collide with each other. The more energy with which the two particles collide, the stronger the reaction will be. So obviously an atomic bomb reaction is way stronger than iron nail rusting. That energy that's released from an atomic reaction, which is an exothermic reaction, is a lot stronger than what's released during a nail rusting because of the amount of energy that it deals with. Okay, so in order for a reaction to occur, you have to have what's called an activation energy. This is the minimum amount of energy necessary for a chemical reaction to occur. So chemical reactions have to just have a base amount of energy for those atoms and compounds to collide. So now let's look at how fast those reactions can occur or how slow. That is called the rate of reaction. It measures how fast a reaction is going to occur. So if the number of collisions occur really fast, then you've got a higher rate of reaction. So let's take a look at these characteristics. Let's say I increase temperature. If I increase temperature, notice how fast those molecules are now colliding. So temperature will increase the rate of reaction. Let's look at pressure. If we increase pressure, notice how often those molecules are colliding. That will also increase the rate of reaction. So there are ways to speed up how fast chemicals will react. And the ways to do that are through, one, temperature. It increases the rate because the faster the molecules are moving, and remember, if you increase temperature, that means those molecules have more kinetic energy. So they're going to move around a lot faster and there's going to be more collisions. That's why you use freezers to decrease the rate of reaction and prevent spoiling. So let's take a look at what that looks like. All right, so in this example, if we increase the temperature, well, let me see if this is going to work. There it goes. Okay, so there you have different molecules. And when they snap together and you see that little bright snap, that means they reacted. So let's look at if we increase the temperature. How do I increase it? Why isn't it increasing? Oh, here we go. Way to go, Miss Stevens. Uh, hold on. Got it. Okay, so now I increase the temperature. Notice how fast the molecules are moving and how often they collide. So temperature increases the rate of reaction. Okay, if I slow it down and add the same ones, they don't react very often. But if I increase that temperature, they're going to react a lot more often. See how quickly they're reacting? Okay, so temperature is one way that you can speed up the rate of reaction. Remember, you can also slow it down if you take away temperature or take away kinetic energy. The other factor that's going to determine the rate of reaction is concentration. That's how much the amount of the molecules present in a certain volume. If you have more present, that's going to increase the rate because there's more collisions. So let's take a look at what that looks like. Okay, so what you've got is each bottle has what we call molarity. That's how highly concentrated it is. We've got 0.5. Notice they're not reacting very often. So now let's switch it. We're going to reset it. And we're going to go up in concentration. Notice the rate of reaction increases because there's more of them to hit each other. So you have more collisions the more concentrated a reaction the molecules are. Okay, and the last thing we're going to look at is surface area. So surface area will also increase the rate. So let's talk about a twig versus a log. A twig has more surface area because there's more mass that's located on the surface than a log. So it's going to burn faster than a log. So let's take a look at that. All right, so what I have here is different surface areas. I've got a thick, looks like a sugar cube. So it has a very low surface area. So watch, it takes a while for it to react. Okay? So now let's reset it and let's do a little bit bigger surface area. A lot quicker for all the compound to react. So now let's do the largest surface area. Look how quickly it reacts. Because if more of the compound is located on the surface, it's going to react with what's in air. That's why if you take a thick piece of iron and it's really thick, it's going to take a lot more time to rust than if you take a nail that's really thin. So those are ways that we can increase the rate of reaction. Now sometimes we don't want reactions to occur quickly. So we use what's called an inhibitor. That's going to be a chemical that slows down the rates of reactions. So butyrate hydrotolacine, BHT, slows down the spoiling of cereal and increases the shelf life. So that's a chemical that's put on cereal, and yes, it's okay to eat it, and that's going to slow the rate of spoiling so that you can keep that cereal in your pantry longer. Then you have something called a catalyst. That's a chemical that's going to speed up a chemical reaction. So what a catalyst does is it reduces the amount of activation needed to start a reaction. I think of a catalyst as like a matchmaker. For example, a matchmaker is somebody that you hire, somebody you know who goes out and knows you and other people and brings you two together. It's kind of like what they have you see all the commercials of Match.com, the different dating websites. Okay, so it reduces you don't have to put as much energy to go and find a match as you would if you were just by yourself going to different places and trying to find your match. So that's kind of how I think of it. Another way to think of it is that it provides an alternate pathway. So for example, which is easier, to hike all the way up and over the mountain or go through a tunnel? Okay, a catalyst gives you a different route, and that's how it lowers or reduces the activation energy. Because you're going to exert less energy going this way, going through the mountain, than going over the mountain. So that's what a catalyst does, is it reduces the amount of activation energy necessary to start a chemical reaction. Then you have an enzyme, which is a type of catalyst. It's a large protein molecules. We have enzymes in our saliva that are going to help speed up reactions. So if you look here, the enzyme, where is it at? I think I have to click somewhere. Okay, and the enzyme is a big compound, okay, that actually grabs other compounds and allows them to react. So it also reduces the amount of activation energy. So here are the compounds that need to react. So an enzyme is going to go grab them and place them together. Okay? And that's what you see in blue, is it's bringing the red together and allowing them to react. Oops, wrong one. Hold on. Okay, so now you should have an idea of ways that we can increase rates of reaction to allow those chemicals to react faster, and ways that we can slow it down.